Greetings to you. Welcome to Physics with Ben. In today's video, we'll be looking at sound waves, vibration in strings and pipes. Waves. A wave is a disturbance that travels through a medium, transferring energy from one point to another without a permanent displacement of the medium itself. Based on the material medium with which a wave needs, we have two types of waves, namely, we have mechanical waves and electromagnetic waves. Mechanical waves are those waves that require a material medium for their propagation, for their transportation. Example of such waves, we have sound waves. We have waves on the rope, that is waves on the string. When you are playing a guitar, you are generating mechanical waves. Waves on water, waves in water. When you drop a stone on the water and you see some ripples, we call them water waves. They are all mechanical waves. How about electromagnetic waves? Electromagnetic waves are those waves that do not require a material medium for their propagation. Example of such waves are what I call Rami Vusga. Ra, mi, Vox, Ga. As science students, it is expedient we derive acronym in knowing some of the things we need to know the way they are. So Rami Vusga here, your RA stands for radio waves, your M here stands for microwaves, your I stands for infrared rays, and your V stands for visible light, your U stands for ultraviolet rays, your X stands for X-rays, and your GA stands for gamma rays. Visible light, this is where you have ROI B, yes. Visible light, this is where you have your ROI B. You have red light, you have orange, you have yellow, you have green, you have blue, you have indigo, and you have violets. All these, we call them electromagnetic waves. These waves don't require a material medium for their propagation. Please take notes. For the sake of this video, we are not going to look at AM waves. We are concentrating on sound waves. So what are sound waves? Sound waves are waves that are produced by vibrating particles. If I hit my hand on the table, you hear a sound. I have set the table into vibration, and then you hear that sound. The air molecules around this vicinity that made it to hear that sound is the material medium that is responsible in transporting these sound waves to your ear. So the air molecules are the material medium with which sound waves will be propagated through. Sound wave is a longitudinal waves. While all the waves are listed here, Rami Vusga and the Rugby, they are all transverse waves. Transverse waves are those waves that travel perpendicular in the direction of travel of their propagation. This is a pictorial representation of transverse wave. All Rugby, all Rami Vusga waves, EM wave spectrum, they travel in this pattern. However, sound wave is a longitudinal wave that travel like this. Waves on the spring are examples of longitudinal waves. You see that? When you see a millipede trying to walk, that is a perfect example of how sound waves travel. They compress and they expand. They compress and they expand. They compress and they expand. So we have something like this. We have something like this as a pictorial representation of how sound waves are. And then we call this these are compression and what? Expansion. So this is how you can represent sound waves pictorially or graphically. So we are going to look at the properties of waves. There are 5 main properties of waves. We have reflection of waves. The examiners will always ask you this: reflection. We have refraction. We have diffraction. We have interference. We have polarization. There are questions that why is it that sound waves are not polarized? Of all these properties, polarization is not found in sound waves. Sound waves don't carry this property. These are the properties of sound waves. We have this as the properties of sound waves: reflection, refraction, diffraction, interference of sound waves. We are going to dwell chiefly on this. I will touch this quickly. Reflection of sound wave. Here we have what we call constructive interference and destructive interference. Both of these interference occur when the wave is traveling, when 2 waves are traveling from a source and they end up having the same amplitude, the same wavelength, the same speed. In that case, interference of wave will take place. Do you understand? But we are not looking at this right now. I want to concentrate on reflection of sound waves. Reflection of sound wave is simply the bouncing back of a sound when it hits a reflecting surface. I mean, when it hits a plane surface or an acoustical wall. We call it echo. So if I chose this to be my wall, and somebody is standing here to shout. This guy will produce sound, and the sound will travel from this to this with a D. The sound will travel back again with a D. So we say that going here and coming back, we have 2D. Because this D and this D, the distance is the same thing. So, but for you to hear distinct sound and distinct echo, the distance with which you are standing, where the source of the sound is produced, and the wall, the distance must be 16.5 meters and above. If not, echo will not occur. So if you can recall very well from V is equals to F, V is equals to F lambda, V is equals to F lambda. We call this the general wave equation. And this equation we use chiefly in this topic. I would like you to also know that sound wave has velocity in air, velocity in water, and velocity also in still media. In all this media, the velocity is not the same. The velocity of sound wave in air media is about 3.2 meters per second square. The velocity of sound wave in air media is about that, and the velocity of sound wave in water is about 1,500 meters per second. And then the velocity of sound wave in steel rod is 5,000 meters per second square. The velocity of sound wave in steel rod is that. The velocity of sound wave in water is that. The velocity of sound wave in air is that. The reason why I am writing all this is that they will give you a equation sometimes and they will not include the velocity. But then the measure with which the sound was produced will be stated in the equation. So it is left for you to know that, oh, if it is in air media, this is what I have. And if it is in water, this is what I have. And if it is in steel rod, this is what I have. So we are going to generate the equation for sound wave, for echo. The equation for echo. Recall that your velocity v is given as distance all over time. Oh, since we are using d here to represent our distance or displacement, we're going to clean this x and write a d here. So since echo has to do with two distances, the distance going, that is the incident ray, the incident sound wave, and then the reflected sound wave. We have 1d and another d, giving us 2d. So for this reason, we can write that the equation for echo is given as 2d all over time. This is the equation we are going to use in this video shortly to calculate echo. We want to look at the two more things: intensity of sound and the loudness of sound. Intensity of sound wave and the loudness of sound. The intensity of sound is given as I is equals to I naught all over d squared. Some textbook would write it as E is equals to E naught all over d squared. Yes, E is equals to E naught all over d squared, or I is equals to I naught all over. Yes, you can use R here, R squared or d squared here. And this is what you have in your new school physics textbook. Both of them, you can use any of them. So this is the intensity of sound wave. What is the meaning of this equation? The intensity of sound wave is also given as I is equals to power all over A. And this A is given as your 4 pi r squared. So it implies that the intensity of sound wave is also given as power P all over 4 pi r squared. 4 pi r squared. Now, I want to explain the meaning of this equation. We call this the inverse square law. If you can go on the internet and Google, you can find some of these things in your new school physics textbook. I use so many textbooks. The other video I was telling you that as a teacher I will always recommend this book to you. Now I'm telling you that this textbook is another wonderful textbook that you need to use. Another one I will recommend to you in today's video is Today's Physics. Today's Physics. Go and check it out. You see it and get it for yourself. So this is what we call the inverse square law. The inverse square law. The inverse square law explains that I naught is the sound, is the intensity of sound wave at the source. If I draw a speaker here and I draw a speaker here to represent sound wave, this speaker has a surface area of this. Yes. Can you see this very well? So, what this law is saying is that there is a surface area. There is a surface area here that is expanding. That if the distance from from here to here is 2. What you have is 2 squared. If the distance from here to here is 3, what you have here is 3 squared. If the distance from here to here is 5, what you have is 5 squared. What this law is saying is that the intensity of sound wave is stronger at the source and is constant. Why this I without the source field is the intensity of sound wave at a distance. It means that, and that distance is represented as r, the radius away from this source. It means that if you increase the distance, the intensity of sound wave will decrease. So you have increase, decrease, decrease, increase. Coming this way, the square root of the distance is decreasing and the intensity of sound wave is increasing. Going this way, the distance, the square root of the distance is increasing, and the intensity of sound wave is decreasing. Is that understood? We call this the inverse square law. So if I can clean this quickly, I will throw more light on this. It also means that intensity of sound wave is given as power P all over 4 pi r squared, or power P is all over area. Now, if I is equal to this, and I is also equal to this, then we are free to equate this equation with this equation. I call this the physics of cut and join. I will explain that in a video shortly. So it implies that the intensity of sound wave I naught all over r squared is the same thing as what? P all over area. You can call this your equation 1, you can call this your equation 2, you can call this your equation star, you can call this your equation 3, you can call this your equation 4. So this implies that the intensity of sound wave I naught all over r squared is given as P all over 4 pi r squared. This is the equation for the intensity of sound waves. We want to look at loudness of sound waves. I keep telling my student that loudness of sound wave is a psychological thing. What I would consider as a loud music, you may not consider it as a loud music. So it is a psychological factor. However, there is an equation for that. The equation for, you can screenshot this quickly. The equation for the loudness of sound wave is given as follows. Loudness of sound wave L is given as the log of I. As simple as that. Loudness of sound wave is given as the log of I. And if I is equal to I naught all over r squared, or I is equal to P all over 4 pi r squared, it implies that the loudness of sound is given as the log of P all over 4 pi r squared, or log L is equal to the log of I naught all over r squared. That is it. That is it. So this is the equation for the loudness of sound waves. Having looked at all this, I would like us to quickly look at the topic for the day: vibration in string and pipes. For we to look at vibration in strings and in pipes, I would like us to look at another class of wave based on motion. Classification of waves based on motion, we have two types of waves. We have progressive or traveling waves. We have stationary or standing waves. For you to be able to understand the physics behind the guitar, the physics behind the flutes, the pipe instruments, you need to pay maximum attention to what I am about to explain right now. For a standing wave, you have this. There are two conditions that must come before you will have a standing wave or a stationary wave. Let us look at this as our line, or let's say the line through which the wave will travel. Or let's look at it as, let's consider this as a spring of a guitar. If you pluck this is what you have. A wave will travel this way. I'm going to use black pen now. A wave will travel this way, come down, go up, come down, go up. So it is expected that as this wave reaches here, let me do it more accurate. As this wave reaches here, this wave we reflect this way. The wave will hit here and then reflect this way, come down, go this way, come down, and back to this place. So you can see that there's an arrow this way and then there's an arrow back here. We call this standing wave. Let's consider this point A. This point A and what? Point B. This is what we call a standing wave in physics. Now, there are some terminologies that you need to get yourself acquainted with as we look at this standing wave. If you don't understand what I'm about to explain here, you can't do any calculation in vibration in strings and in pipes. This is very, very fundamental in understanding every calculation in sound waves. Now, this point is called the node. I will put my A this side and my shift my B this side so that I will label them correctly. This point is called the node. This is the node of the wave. So you have a node here, you have another 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 node here. These openings, you have this point as your antinode. Your antinode. Somewhere here is your antinode. This is where your antinode is. This opening that's here. Your antinode. Your antinode. So you have node, antinode, node, antinode, node, antinode, node, antinode, node. Now, I want to explain something very, very important. From this node to this node, the distance between the distance between one successive node is called a loop. From this point to this point, from this point to this point, we call it a loop. From this point to this point, we call it a loop. And a loop is equal to what? Lambda all over 2. Now, if from this point to this point is a loop, it means that from this point to this point is half a loop. And half a loop is given as what? Lambda all over 4. From this end to this A, this antinode here, it is lambda all over 4. That is quarter wavelength. That is 1 over 4 times wavelength. From this point to this point is 1 over 2 times wavelength. So it means that if from here to here is half, from here to here is one full wavelength. Meaning 2 loops, 1, 2. 2 loops will give you one full wavelength. So from here to this point, we call it one full wavelength. How do you get that? There are 2 ways of doing it. You can either say lambda all over 2 plus lambda all over 2, or you can say that pi all over 4 plus lambda all over 4 plus lambda all over 4 plus lambda all over 4. If you do this, you arrive at what? Just 1 lambda. What do you have here? You have 2. So you have what? 2 lambda. So this cancels this. What do you have here? You are left with this. If you do this, what do you have? You have 4 down here. What do you have? You have lambda plus lambda plus lambda plus lambda. What do you have? You have 4 lambda divided by what? 4. What do you have? You have just lambda. So the distance from here to here is 1 lambda, and this lambda is called wavelength. 1 full wavelength. 2 loops will give you 1 full wavelength. Another way to do that is this. You can simply say, since one loop, let's call it, since 1 loop is equals to lambda all over 2, 2 loops is equals to what? 2 loops is equals to what? Is equals to x. You can cross multiply. And you say that your x becomes what? 2 times lambda all over 2. This will go, and you have what? 1 lambda. Do you understand? So based on the loops of vibration, you just use this particular trick and get to the particular loop you are requested to calculate. I believe this is well understood. This is well explained. This is well understood. This is well explained. Now let us look at vibration in string instruments. So in summary, this is what I have from this point to this point. I call it lambda all over 2. And then if you trace it down here, let me increase this down. So from this point to this point is 1 full wavelength. And if you go up here, let me do it proper. From this point to this point is lambda all over 4. Take note of this. 2 loops, 1 full wavelength. 1 loop, lambda over 2. Half loop, lambda all over 4. We call this a standing wave. For you to have a standing wave, you must have a reflecting wave with this black line, and then a reflected ray and a reflected wave with this line. And that wave will have to hit a particular surface, and that is the surface. Let's call this maybe wall or obstacle. This is what you need to know. Now, we want to look at vibration in strings. When I talk of strings, what do I mean?